is our third class, and I just want to recall a problem that we discussed yesterday, but I was not really satisfied with my discussion. So I went through the problem again, and I want to discuss it with you again. The problem is this problem that we have a decay of a muon in a particle detector. You observe a muon, okay? So, because I think that I was not satisfied in the sense that I didn't tell you well what is the data here and what is the model, because everything, sometimes it is difficult to understand in a problem what is data and what is model, and I think this was the difficulty for which I couldn't explain well the problem yesterday, but today it will be different. So we have, the facts are the following. We are in a particle detector and we observe a muon. So the data is the observed muon, okay? And then we have two hypotheses, that the muon originated from a kaon or the muon originated from a pion. So pion and kaon here are the hypotheses, are the theoretical models, okay? Because my hypothesis is this muon that I measure arises from a kaon or from my pion. So these are the two alternative hypotheses, kaon or pion, okay? So my posterior and the problem gives me the probability that the data that I observe, the pion arises, the muon, arises from a pion. So this is the likelihood of observing a pion that has decayed, observing a muon that has decayed from a pion, and the other likelihood is the likelihood of observing a muon that arises from a kaon. Okay, these are both the likelihoods. And also, we know that the ratio of pion to kaon in the original beam of the detector is 3:1. So these are our prior probabilities. Okay? So, what the problem asks is the probability that the observed muon originated from a pion or a kaon. So, the probability is on kaon or pion, because these are the models, pion or kaon. Okay? So, I think maybe it's better right here. So, the posterior probability is the posterior probability that I want is the posterior probability on the pion model, given that I observed a muon. And this would be the likelihood of observing a muon from the hypothesis, given that the hypothesis that the muon decays from a pion is correct, times the prior knowledge that I have about the pion. And this, okay? This is okay? So, and the important thing, because we wanted to discuss this problem, clarifying here the normalization constant, okay? So what comes here is what we call the global likelihood of all models. That would be the posterior of getting, the probability of getting a pion from a muon decay plus the probability of that the pion model explains the muon decay plus the probability that the kaon model explains the muon decay. Okay? And I would write this in this way. It is the likelihood that the observed muon arises from a pion model times the prior probability of the pion plus the likelihood that the observed muon comes from a kaon decay times the prior probability of the kaon. Okay? So this is the normalization constant. If I would have had more alternative hypotheses, let's say 3, 4, n, I have to sum the n posterior probabilities here, okay? Or if you have something that is continuous, integrate, okay, over all your models, okay? We will come back to this idea later on when we talk about Bayesian evidence. These ones, yes, these are the prior knowledge that you have about how many pions you have in your detector and how many counts you have in your detector. I know that it's confusing because I'm talking about yesterday maybe I said that the probability can arise from theoretical issues or from observational issues, okay? In this case, the prior probability is from observational issues because in your detector, before, what are you putting in your detector? Imagine your detector as a recipe of your kitchen, as a recipe. I put 3 pions and 1 kaon, okay? Before I see any muon. So the ratio, the initial ratio of pions to kaon is 3 to 1. It's my prior knowledge of how many I have, okay? Before measuring, okay? Then I measure and see the muon and so on, okay? Yes, yes. Yes. Actually, you don't measure, it's your experimental design. No? When you design a detector, you design, yes, like the initial conditions of your detector. Yes. But in terms of what we were talking is the prior knowledge about this, the prior experimental knowledge. You could have a theoretical prior also. In this case, it's an experimental prior. Okay. Yes.
That here the likelihood that we get for both pions and kaons is highly dependent on the prior knowledge that we have about the ratio of the pion and kaon. So is it always not the case? Like
no, the likelihood, these are the most likelihoods are totally independent from the prior knowledge.
But how can we get these likelihoods without knowing like how much, what is the amount of pion and kaon we have?
This is given by the experimental guy gives you these quantities. Okay.
Let's suppose that I don't know how much pion and kaon I have in my team.
Ah, you're lost. Yes, you have a problem there.
Yes, and how can I get the likelihood? Like because likelihood is explains like how our data is like which model is explaining the data better. That is like likelihood kind of thing, right?
Yes. No, the likelihood is, remember my class of yesterday, is the probability density function evaluated on your data. So it's the knowledge you get after you get your data. And this is totally independent from your prior knowledge about your model. Okay? So this is the difference. So maybe I am not getting your question. Pose it again.
Yeah. So, you saying that like yesterday, like you showed us two plots of some three values. So where the likelihood is maximum is the hypothesis that was like explaining the data points better.
Yes.
So if we combine it here, we can say that we get some data from the experiment and the likelihood we are getting from two hypotheses. Yes.
So Kaon is explains, yes, you're right. Here Kaon is explaining better the muon than pion. Yes.
And we should get that knowledge because we have some theoretical data and like if we, how do we calculate this likelihood? Because if we, I know that I have like the ratio of the pion and kaon is this much and I am getting this data. So how do I differentiate like from big bio.
I understand. Yes, what's here missing, and this is far beyond our knowledge, but by that I thank you the question. So this is a calculation where you have a lot of particle physics, theoretical particle physics there that we don't know about. So the theoretical guy gives you the probability density function, and you just evaluate it in seeing a muon, okay, or seeing a count. So, but the probability density function is built by the theoretical guy, okay? And the experimental guy says that you detected a muon, so you evaluate your probability density function and you get those numbers, and also the experimental guy gives you this ratio.
Never depends on the prior model.
No, it depends, but the problem gives you the result. See, the likelihood does depend on a lot of things that we don't know because we are not particle physics, and the problem is just give you the outcome in a number. But of course, it should depend on a lot of things that are just evaluated here, and you get just the number. But good point. Thank you for asking. Okay. Well, so at the beginning of this class, I wanted to make a brief recall of the class of yesterday, just to be in the same page, because also I felt that it was necessary this recall. Okay. One thing we didn't address yesterday, and I wanted to go back a little bit, not in the, is, or maybe I make this clear, but will you tell me, is that likelihoods are not necessarily Gaussian, okay? I teach how to find the confidence interval in the case where the likelihood is Gaussian, but this is not necessarily the case everywhere, in any problem, okay? And one example of that, one moment please. One example of that is this problem that we didn't address yesterday. And you can see it by yourselves with some care. But the point here is we have any measurements of decay time of the decay time of an unstable particle with mean life tau. Gamma is 1 over tau. Tau is a number that you know, okay? The problem is to use the maximum likely estimator method to find the estimated value of the lifetime parameters of a particle's lifetime. We are not doing this here. My point is just that the likelihood here is the product. The likelihood here is the product of all measurements. And what's more important is that this is not Gaussian at all. It's exponential. Okay, so just to show you a real likelihood example that is not Gaussian, okay, and how you can find the maximum likelihood estimator of this type of likelihood. Okay, well, I just wanted to recall this, and also to recall that yesterday we talked a lot about likelihood, the frequentist analysis. How do I find the confidence interval when I have the likelihood, which is related with the frequentist approach? I also spent some time showing how you calculate confidence interval. And just to recall that for doing this, we made an approximation that the likelihood must be Gaussian around the maximum likelihood estimator. Okay, and in this way, is the way that usually people estimate confidence interval. But you have to check always your likelihood or your posterior probability, which is the Bayesian approach. But in any case, doing Bayesian or framework or frequentist analysis, always you have to check that your posterior or your likelihood is Gaussian. If not, if it's Gaussian, you can apply the usual techniques, and if it's not, you have to do it by yourself. in the way that we define here confidence intervals. And we are going back to this today because we are going back to the Bayesian analysis. Okay, any doubt with you want to ask something about yesterday? Okay. So if there are no doubts, I just wanted to come back here to Bayes' theorem for probability density function for parameter estimation, and recall this is our good friend, the posterior probability of parameter theta, given that I have measured a data set V and I have a prior knowledge of my model given by I. And this is equal to the prior knowledge I have of the parameter theta, which, as we discussed before, can be a prior knowledge arising from a theoretical development or an experimental or observational data. This is multiplied by the likelihood of the data given, assuming that the model is described by this parameter theta, and divided by a normalization factor, which we call the global likelihood. And this this guy will be very important here. This guy is called the Bayesian evidence and will be important at the time of answering the questions that if I have several models that can fit very well my data, which model should I prefer? We will come back to this, but the important thing that here I am just integrating the posterior overall values of the parameter, okay? This global likelihood, in the most general case, sometimes is that if you are in a fixed model, which is this case, in this case we have a fixed model which is described by a parameter theta or could be described by a collection of parameter thetas. But also, it could be the case, just in the problem that we just addressed, that I have alternative hypotheses, alternative models. In this case, the Bayesian evidence is an integral over all models, or a sum over all models, just as we did before, summing the posterior of the kaon and the posterior of the pion. Okay? Good. So, we talked about priors. It was the last time we talked about priors. And, okay, now I think that maybe you're getting a little bit bored here because I am going to define again what is a confidence interval, but now in the Bayesian framework. Maybe I have been, since my first class, I have been giving a lot of definition of confidence intervals, and all sound like very similar. But there are subtle details, so please pay attention to those details, okay? Because when yesterday I talked about confidence intervals in the frequentist approach, I was talking about differences in the likelihood. What is the value of the likelihood such that there is a difference that makes that I have under my curve the 68% of the parameter space. But now I am going to define the confidence interval taking the posterior probability, which is the important guy in the Bayesian framework, okay? And maybe you could say, okay, but if you have a uniform prior, likelihood and posterior are the same, and in most cosmological analysis, this is the case. Okay, but in some analysis, it can be different, and this is why we are scientists, we are not mechanical people, so we have to know how to differentiate among different problems. We cannot take the tool without knowing anything, without criterion, and just applying it to the problem at hand, okay? And this is for everything you do in your PhD or your career as researchers. Okay. So the information you give when you study the posterior can be summarized by the most probable value of the parameter, which is the maximum value of your posterior distribution, or the mean value, which are not the same, not necessarily the best fit value or the most probable value is the same as the mean value. And you will see in the papers sometimes that people quote the confidence interval and also the best fit value. And you will see that the best fit value is not necessarily in the middle of the confidence interval. This is the reason, and this happens when your posterior probability is not Gaussian. The mean value is defined in the same way that I defined mean value for probabilities in my first class. It's just the integral of the posterior probability that describes the posterior probability, the probability of the parameter beta, integrated in multiplied by theta and integrated in all the between minus infinite and infinite. I'm sorry, I didn't put it. And the confidence interval of the parameter theta is defined as the region for which the confidence interval for a certain probability C. Note that here I am generalizing. This is not necessarily the 68%. You can put there whatever you want, 68, 95, 99, whatever you want. So, but the idea is the same. The C percent probability region is the region for which, if I integrate over that region, the posterior probability, I get the value of C. Okay. Yesterday we also talked about nuisance parameters. That is, parameters that are not relevant for my analysis. And I would like to recall that this is really dependent on the person that is performing the analysis. And I give the following example that I think I gave it yesterday, but I will repeat it. For example, in the CMB analysis, you have cosmological parameters, but also, remember, CMB analysis, you are analyzing the CMB maps without photons that reach Earth. But these photons are, we suppose, that are photons that come from the very early universe when neutral hydrogen formed. Before of that, because before of that, the photons and electrons were interacting with each other via Thomson scattering, so no photon could travel. These photons were trapped. When neutral hydrogen is formed, the photons are free to travel, and the wonderful thing is that we can, and they travel freely to the universe, and they have a lot of information about the physical conditions and so on, and we can detect them. But there is a problem there, because unfortunately, the photon doesn't come with a flag that says, I am a CMB photon, because there are other photons that come here from the galaxy or from other galaxies, and the other photons also don't come with a flag that say, I come from Andromeda, I come from the Milky Way, I come from the sun. So it is our task to distinguish those photons, and as a matter of fact, this is an important problem, a very important problem in CMB analysis, to distinguish programs from what we call foregrounds from CMB photons. But my point here is the following. For me, as a cosmologist, the people make models to subtract the, so the CMB experiments measure all the photons, and then people make models to subtract from the maps what we suppose that are photons that come not from the early universe. But as a cosmologist, I'm not interested in those parameters that model the foregrounds. But an astrophysics could be. So for me, the parameters of the foreground models are nuisance parameters, but for the astrophysics, the cosmological parameters are nuisance parameters. Okay? So, how do we deal in the Bayesian analysis with these nuisance parameters? Well, what we do is we do not do profile likelihoods as in the frequentist analysis, but we do is a marginalization of our posterior probability. That is, if my posterior depends on two parameters, theta and phi is what I consider a nuisance parameter, I integrate overall between minus infinity and infinity the posterior probability in phi, and so I get a posterior probability only in theta, okay? And so I get rid of that parameter. Okay, of course, in most cases, my posterior probability does not depend on a single parameter theta, but on several parameters theta. And in that case, the confidence interval are defined very similar, but you define it over this posterior probability that has many parameters. In the case of the two-dimensional confidence contours that are the ones that are shown in the papers, if you have many parameters, you cannot do this directly. You first have to integrate. So this is to say a confidence region in the n-dimensional space, but you cannot visualize this. We only can visualize well the confidence region in a plane. So what you do is you integrate about around the parameters you do not want to plot, and then with this marginalized posterior probability, you calculate your confidence regions as we are used to do. Okay? Maybe this is a little confusing, so I will change a little bit the PDFs to make it more clear, because now that I explain, I see that this is confusing because it seems that in the two-dimensional region, you're integrating a probability of many parameters, and this is not like that. Here, if I want to make a confidence region in the plane, I do not have three parameters. I integrate in all the parameters that I want my confidence region. So if this is a two-dimensional confidence region, this is the marginalized posterior probability, where if I want the confidence region in theta 1 and theta 2, I have marginalized integrate in the rest of the parameters. This is not clear here. I would make the PDF clear after the class of today. And I recommend you that maybe next week download again all PDFs, because of course there will be typos and I will be correcting them. So to have the best version of this course, download all the classes again next week. Okay. And well, and this is the same here. It should be only one parameter. So well, some remarks just to recall. The Bayesian approach does not provide a point estimate for the parameters at the frequencies framework did with the maximum likelihood estimator. There is not such maximum likelihood estimator in the Bayesian analysis. Also, something important that we already discussed today, but it is good to recall, is that the Bayesian approach allows us to incorporate prior information about the parameters, which can be useful when we have this prior information. In some cases, we can have no information, and if one has no prior information, what does apply is the uniform distribution. Your prior information is a uniform distribution, that is that any value of the parameter has the same probability to appear. The meaning of confidence interval is the Bayesian approach is different from the frequentist approach. We discussed here this a lot, but this is just to stress. In the Bayesian approach, the confidence interval is a region where the parameter has a certain probability of being found, while in the frequentist, it is a region where the parameter would be measured, or would be found in a certain percent of repeated experiments. Okay. And this is the idea, but I think that I have not to go back here because we discussed this enough in the first class. So we can move on Okay, this problem, I want you to do it as a task for the exam, and if we have some time tomorrow, we can discuss it, or you can ask me, okay? But I will not spend time here because we have many things to discuss today. So now I am moving. Are we making coffee break today, Joanny? Okay, at what time? So to calculate. 11:20. Okay, we have plenty of time. So now we are moving to one of the questions that I posed the first day, my first class, that is, if I have several models that explain my data well, which model should I prefer? Okay, and for this we have tools, because so far we have only analyzed the case when I have only one model. Well, maybe the exception was the pion count problem where you had two models, okay? But these were probabilities, discrete probabilities, not probability distribution functions, as the ones we use in cosmology. So in the Bayesian framework, this model comparison is done using the Bayesian evidence, which is defined in this way. You can just, here you are just integrating the likelihood multiplied by the posterior. But there is a slight difference here in the notation that has to do that here I am labeling the model and also the parameter. Okay, the model can have different parameters. So this is the integral over all models. Okay, it's the integral of the parameter. Sorry, no. This is an integral of this is an integral for a fixed model, and you will be performing such integral for all the models that you want to compare. Okay, and if your model has more than one parameter, you have to integrate this over all the parameters of your model. Okay, so at the end of the day, this is a global likelihood for a fixed data set and a fixed model. Okay? So the Bayesian evidence, what gives me the comparison between models is what I call the ratio of Bayesian evidence. The Bayesian evidence of model 1 for data D divided by the Bayesian evidence for model 2 for the same data set. Okay? So I calculate this ratio, and I know that if this value is greater than 1, this indicates that model 1 is more likely than model 2, while if the value of B12 is less than 1, that indicates that the data prefer model 2 over model 1. This preference, the degree of preference, can be quantified with what is called the Jeffrey scale, which is an arbitrary scale. I have to say it's totally arbitrary. It's a scale that a guy put and everybody applies, but it has no. It has some sense, but it's not very. How to say. It has not an analytical derivation. And the Jeffrey scale tells you if you have weak preference for your models, moderate evidence, or strong evidence. Okay? And if you read papers of homology, you will see that. An important point about Bayesian evidence is that it is very time consuming. It consumes a lot of computing time. Usually it is performed via nested sampling or thermodynamic integration models, and you use a lot of time for this. And sometimes you don't have access to so much time. So in this case, you can use other other criterions that are maybe not that strict. So I would prefer always to calculate the variation evidence, but in case you can't, you can use these criterions that I will describe now. But before describing this, something I didn't say about is that sometimes sometimes not, most of the times, the models that you consider have different quantity of free parameters. For example, Lambda CDM has, vanilla Lambda CDM has 6 parameters, and CPL has 2 more parameters. And if you have a scalar field, you will have 1 parameter for the potential, or maybe 2. It depends what you're considering. So the question that one wants to answer is, how do I compare likelihoods with different number of parameters? And for this, these criterions are built for this. So there is the archaic information criterion that what you measure, you calculate for your model is 2k minus 2 times the logarithm of the maximum likelihood, where k is the number of parameters. So here, this criterion is penalizing, so you can have the same value of the likelihood, but for different number of parameters, and this criterion penalizes with these terms the number of parameters. Then there is the variation information criterion that also penalizes for the parameters, but also for the number of data points that you are using in your analysis. And finally, there is the deviance information criterion, which is expressed like this. And here, this guy is minus 2 times the logarithm of the likelihood, and this is the average deviance of the posterior distribution. And this guy is what we call the deviance at the posterior means. These are really very easy to calculate, and this is the reason for which most of the papers use this criterion. But there is a lot of discussion about this because some people do not trust well in your criterion. So the best thing you can do always is to calculate variation evidence. This is just if you're not able to do this, well, you can give this criterion. Yes, these are the variation. So usually it's the variation evidence, or you can quote any of these criterions. Well, there is no criterion to decide this. Usually, it depends. For example, if you have a large number of data, if your data set has a large number, then this criterion would be preferred. If your data set have a small number of data, you should use this because you penalize, you're taking in account this, okay? And the deviance criterion, I haven't used it much, but I think that people use it, but I don't know exactly when it is reasonable to apply it. Usually you will see in the paper these 2 criteria. Okay, I forgot that I have this nice instrument, and I don't need to have here our support. Yes. Yes.
So this is an engineer for parts.
Yes.
What do you think about?
Okay, thank you for the question. What you're doing here is, this is a number that gives you, you calculate this for the 2 models, okay? And the lower model is the the lower value is the value that you will prefer. So, for example, if you have the same likelihood in Lambda CDM and in CPL, Lambda CDM is winning because you don't have this term here.
Can you give a result, for example, in one model and another criterion in favor of the other model?
Well, for this, if you have a large number of data sets, you will prefer this one, and if your data set has not such large number, you will prefer this one. Okay. Okay. I think I have been lying you. It's exactly the opposite. I'm sorry. And it was here. It's the opposite. The archaic is the most appropriate for small sample sizes, and the other one for large sample sizes. Okay, I'm sorry, I got confused. But the point is the sample size. Okay, and here the class reminded me that the last one is a variation approach that takes into account the uncertainty in the parameter estimate. Okay, which the two other criterion did not. So I think this is a very nice criterion also. Usually we quote everything, okay? And if always when I do this kind of analysis, I define what is a baseline model, my base model. That is usually Lambda CDM, okay? And so what we do is to calculate the difference in the between the baseline and the model you are testing, the scalar field, CPL, modified gravity, whatever. Okay? So if this difference is greater than 1, this favors the test models, and if the difference is lower than 1, this favors the baseline models. And you also have a Sheffield criterion for this that indicates the degree of preference, strong, weak, or moderate. Okay? So if you have, for example, if my final result is that I have a weak preference of my model over Lambda CDM, I cannot claim that this model, that the data will prefer this model, because my model has more parameters, maybe have other hypotheses that have not been checked, or I have to argue why this model is better than the other. I only can claim that my model is better based on the data, or that the data are preferring this model if I get moderate or strong evidence from these criterions. Okay? Okay, and here also, the deviance information criterion is maybe of the three of these the better criterion, because it uses the entire posterior distribution just rather than just the maximum likelihood estimate. So this is important for Bayesian hierarchical models where the effective number of parameters may be less than the actual number due to the prior constraints. And well, this is the end of lecture 3. And now we are going I'm sorry. And now we are going to official lecture 3. A moment. One moment. Okay. So now Okay, so far, all we have. As you know, I'm not used to the microphone. So far, we have discussed a lot about confidence intervals, frequencies approach, variation approach. So I think, so everything is prepared. So you have all the theoretical tools and conceptual tools to perform your analysis, either frequencies or variation. And what comes today is just a tool to perform better variation analysis using Monte Carlo techniques. Monte Carlo techniques are, we call Monte Carlo techniques to a wide collection of statistical methods based on random numbers that allow us to perform mathematical and statistical calculations that are difficult or impossible to do in an analytical way. So you will hear about Monte Carlo in a lot of by a lot of different researchers. So you call Monte Carlo methods to a lot of different techniques. In our case, if I have many parameters, I have to integrate the posteriors, and this is very difficult to perform. And this is why we use Monte Carlo method. So for cosmology, and also the goal of this course is to teach how you use Monte Carlo, Markov chain Monte Carlo, which is a technique for sampling your posterior. So your posterior now, you know how to build it. You compute the likelihood times the prior. You have your posterior. If I give you the data set and I give you the model, you know how you build your posterior. The problem is that you have to sample this, you have to perform integrals over your posterior. And this is not very easy to compute. So for this, Markov chain Monte Carlo provides a very efficient way to sample the posterior in a multidimensional parameter space. My idea here is not to go straight to Markov chain Monte Carlo, but to give an insight of the most important Monte Carlo technique to get a flavor of what a Monte Carlo technique is. And tomorrow we are going to learn about Markov chain Monte Carlo. Okay, so the class of today will be a little deviation from frequencies and variation analysis and confidence interval. It will be more technical if you want. Okay, so okay, the term Monte Carlo refers to the Monte Carlo casino, one of the capitals of game of chance, as you probably know, and was chosen for this technique due to the inherent randomness. The method was originally developed by Stanislav Ulam and John von Neumann, and a light numerical method that relies on evaluation at endpoints in an m-dimensional space to produce an approximate solution. The Monte Carlo method has an absolute estimation error that decreases as 1 over the square root of n according to the central limit problem, and this is why this technique is computationally easy and feasible. Okay, now I come to, well, the first Monte Carlo technique that I will present is one that I liked a lot when I was preparing this course, because it allows you to calculate the number pi using a Monte Carlo technique. And this is based on the following. If you have this circle, which has a whose radius is equal to 1, and this square, if I calculate the area of the circle and I divide it by the area of the square, I get pi over 4. Okay, this is geometry from kindergarten for you. Okay, so how do we calculate pi with a Monte Carlo technique? What I do is let me make here one parenthesis, because I should have to talk about sampling from a distribution. I think yesterday I talked a little bit about that, but we will recall this today. What is sampling from a distribution? I have a distribution that can be whatever distribution, polynomial, Poisson, binomial, Gaussian. And so I take a random number, but this number, I have some probabilities for the number. If I have the uniform distribution, every number has the same probability to appear. If it's Gaussian binomial, the probabilities will be different. Okay? And those who have been doing your homework, at the end of the first notebook, I put some lines to sample from the uniform distribution, to sample, you have read from the Gaussian distribution. So it is not that you have built, you have to build your sampler. The libraries already have samplers, so you can sample from your distribution. So throwing needles, the idea here to calculate number pi is that, so now I go again to the idea of calculating the number pi from the ratio of the area of the circle to the area of the square. And it is like that. Suppose that I throw needles, random, throw needles in this square. No, I am limited to the square. If I throw, and then I count, what are the quantity of needles that are within the circle, and what are the quantities of needles that are outside the circle? So the quantity of needles and this ratio will be proportional to the number pi. Okay? And this, you can perform it. I will show now how we do it. This, you can do it very easily with this sampling from a uniform distribution that is in your library. So I will show you the notebook here. And the idea is that you play with the notebook, but also you will have to, you will need to have some homework. So, okay. Well, first I upload the libraries. See here, this is the method of throwing needles. I define X and Y as a sampling from a uniform distribution between -1 and 1, n needles, okay? This line means this, and then the needles that are within the circle are the ones for which x to the square, I to the square are minus or equal than 1. And then I sum all these needles and I divide it to the total quantity of needles, okay? And then this is the way of getting pi. I also can calculate the error, but before of this, we are going to play, which is the most fun thing to do. No, I have to. When this happens, it's because I haven't defined the method, okay? So again, here I am throwing 1,000 needles. So if I put some 1,000 needles, do you think I'm going to get a great estimate of pi or not? With only 1,000 needles. Yes or no? No, so good. I have to enlarge the number of needles. Okay, let's do it. I put 1 order of magnitude more. Oh, it's not better, doesn't it? But I can do better. I can put more needles here. And this looks much more better. But there are still some points that are, so I can put 1 0 more. And I think this is very nice. Well, the idea is that you play with this. And here, these methods allows you, because because you always want to get your estimation of pi and the corresponding error. Okay? This is a binomial process. This is a random process. This Monte Carlo technique is a random process that is well described by the binomial distribution because you have two possible outcomes, circle or square, inside the circle or outside the circle, okay? So the error is defined by the binomial distribution. I will show it in a while. It is defined in the PDF, but I don't want to go back right now. So this method allows you to calculate the, so what I really do to estimate pi is to throw needles many times. So I perform the same experiments many times with the same amount of needles, and then I get a mean value and a standard deviation of pi. Okay? And then I can play, the idea is that you play a little bit with this quantity to see what quantity of points and of proofs you need to get a better estimation of pi. And the problem, the exercise you should address is the following. For a fixed value of proofs, well, I'm sorry, this is in Spanish, calculate the value of pi such that the standard deviation is less than 10 to the minus 5. For this, some programming skills are necessary, okay? So those who are not that familiar, please, we can discuss this tomorrow, okay? Because this is a little more difficult than the first notebook, okay? But the idea is to, of course, increase a little bit the difficulty. Okay, then there are other two exercise that have to do with the integrals that we are going to talk later. Okay. So well, any doubts here? Okay. So we can return to the class. Okay, as I said before, the variance of the number of needles is related with the variance with the of the binomial distribution that, if you remember, is the square root. The error is the square root of the variance, and the variance was n. N is the quantity, is the total need, the total quantity of needles that I am throwing, and zero. I'm sorry, and zero is the total quantity of needles that I am throwing, and n is are the positive occurrences that in this case I define as the needle that fall inside the circle. Okay. And the probability, because if you remember in the binomial distribution, this is equal to the square root of n0 times p times 1 minus p. So here p is the probability that you get, or the number of appearances of needles within the circle over the total needles. That would be n over n0, okay? I call this epsilon here. So delta n over n, so this is the way I define n, and delta n over n. Of course, the more similar the area of the circle is to the area where the needles are thrown. In some cases, people don't define a circle, but an hexagon or a polygon with a lot of a pentagon or something with a lot of lados. Okay, you understand what I mean? And the more lados you have, the more the better you will recover the number of pi. In the case you are not doing this with a circle, but with another figure. Any doubts so far? Okay. Same idea. of calculating pi as the ratio of the needles that fall inside the circle, so over the total quantity of needles, can be applied to the calculation of integrals. So imagine now the following, that I want to calculate the area under the circle, under the curve, okay? So with the same idea as calculating pi, I throw needles in this rectangle, and then I count which one falls within the shared area over my total number of needles, okay? And so there is, if my quantity of thrown needles is large enough, I will be able to calculate appropriately this integral. And the integral will be equal to b minus a, the maximum value of the function times n over n0. Okay? So this is the naive way of calculating integrals with Monte Carlo methods. And here, good morning. And here we are making our first approach, our first flavor to what a Markov chain does mean. Remember that our goal is to understand Markov chain Monte Carlo. Okay? This is a Markov chain Monte Carlo, but not the ones we use for cosmological analysis. This is very similar, and it's a flavor to introduce it. So instead of generating these n random points, which imagine that I have a multidimensional integral, this is highly time-consuming. Imagine that now I am generating a Markov chain. The definition of a Markov chain is that each point depends on the previous point. So the points are generated as follows. The point xi plus 1, so the next point, I began with some arbitrary initial conditions, okay? And my next point is generated with random numbers. So I put a random number, okay? And so for each step, I check. If xy, here it should be xy plus 1. This is bad, I'm sorry. xy plus 1, I check if it is within the interval that my original interval, because of this randomness, if I am very close to the limits of the interval, xi plus 1 can fall outside the interval. We don't want this, okay? We want that your needle is in the interval, or the Markov chain falls within the interval. So you check first this, and you also check that I plus 1 is between 0 and the maximum of the function you want to integrate. So if this condition is not satisfied, I go back to the original point, because I don't want this point of my chain, because it's not going to be good for my integration. But if the condition is satisfied, first I check this one, and then I check if Iy is less than f of xy. This is also important. And if this condition is satisfied, I count it as a hit. And then I generate a large number of this chain, and then I count how many points are within the area that I want to integrate over the maximum points, and this is the way I can calculate integrals with Markov chains. Well, this is the same I said, and so far it is clear, because I am changing a little bit the subject now. So if you have any questions, this is the time to ask them. Okay. So we went first. We throw needles in a circle and a square to calculate pi. Then we say, oh, okay, this is a good idea to calculate naively the area under the curve. We can also throw needles and count which needles fall within the area of the curve and outside, and then I can have a good estimation. But this is in a multidimensional space. This can be this can be very time consuming, so it's not convenient. So a Markov chain could do this work, this job better. Okay, so these are the three alternatives to calculate integrals in a naive way. But another thing that is much of interest of we cosmologists is the calculation of mean values, for example, of some function. You want to calculate your function weighted for some probability, okay? And for this, Monte Carlo methods are very useful and less time consuming. So first, we are going to calculate these statistical indicators with what we call naive Monte Carlo. And the nice thing about this is the following. It can be shown, and this is shown, I would say experimentally, but when I say experimentally, I am talking about a computational experiment, no? There is no experimental design here. Just do it in your computer and check if this works. Okay, so you can say you can see that if you want to calculate this integral is can be very well estimated, making this algebra, that is summing the summing endpoints of f, and where, and this is the important thing here, where these points are sampled from this distribution. This is the key concept in Monte Carlo integrals. Okay, you understand what I mean? So if this P is a Gaussian distribution, you sample from the Gaussian distribution. If it's binomial, you find sample from the binomial, and so on. Okay, good. But it can happen, and it usually happens, that it is not very easy to sample from some arbitrary distribution. And also it can happen that the distribution you want to sample is not good to calculate these integrals. So you can perform a trick here. That is the following. You multiply and divide your integral by some function of q. Then we will see what function can be convenient. And then what I do is I sum over p. So my integral now can be calculating summing n values of this whole function where xi is sampled from the q distribution. Okay? This is called Monte Carlo method with importance sampling, and it's much used in Monte Carlo estimations, and in part of your homework is to perform such an integral. Okay? And I will give you an example of a specific function. For example, I want to calculate this integral, okay? So this integral is equal to this expression, but I decide that this is the function I am going to sample, so this integral will be equal to summing endpoints, evaluating this function in endpoints, where these endpoints are evaluated, are sampled from this distribution. Okay? And one important question that one can do is, for example, I want to calculate this integral, okay? Suppose that when I do this, when I sample from e to the minus x, I don't get good results. I see that I don't get good results. I enlarge my number n a lot, and no way. You don't get a good estimate of your integral. So what can I do? I can think, okay, what about doing this with important sampling? I postulate my function g, but all the science here is to know what is the appropriate function g to choose. So I will give you an example, but in the real life, you will have to search it for yourselves. So the function I want to the integral I want to calculate is the area under the curve of the green curve. Okay. Initially, I sampled from the red curve, and I didn't get good results. Okay. But then I decide if my function g, for example, is this one. You see that this function, that sampling for this function, will give you, for sure, a much better approximation to the total integral, okay? Because this function approximates better to the real function that I want to integrate. And you could do it even better. You could work a little bit more and find another function which approximates better to your integral and sample from the sub function, okay? And another question could be, what about, because the libraries that we get in Python and so on are only for sampling from specific distribution, Poisson, binomial, Gaussian, exponential, but they are fixed functions. What happens if the appropriate function from which I need to sample is an arbitrary function, which I don't know how to sample from it? There are techniques, and we will go for that in a minute, to make this connection and make some transformations so you can sample from a known distribution, from a uniform distribution, and make transformations of your samples in a way that the transformed sample is a sampling from the function that you really want. Okay? So I thought, well, there are 10 minutes to the coffee break, so I will begin with this. Well, here this is also in a notebook, that is the instruction how you sample from the uniform distribution, the normal distribution, and the exponential distribution. Of course, be careful with the parameters, okay? Because, and the details, okay? Because everything, as you know, is in the details. Here, this is sampling from a uniform distribution between A and B endpoints. When you sample from a Gaussian distribution, you need to specify what? Mu and sigma, okay? And some details, when you sample the exponential function and you give this number b, this means that you are sampling over 1 over b e to the minus x over b, okay? There is a normal, b is your normalization here. Okay. Okay, so this is going to be a little bit theoretical, but theoretical, but I think you will get it. So the problem consists now of obtaining samples from the distribution f of x using samples from the uniform distribution. Remember that in my first class, I talked about the cumulative distribution function. Okay, here's our good friend, the cumulative distribution function. And we will use it just for this, for obtaining samples from the distribution I like from samples of the uniform distribution. And this is based on the fact that I postulate that the cumulative distribution function of f of x, that is the integral between minus infinity and some value of x, is equal to can always be equal to the integral between minus infinity and some value of the uniform distribution. Remember, the uniform distribution is always 1. So this is equal to R, okay? So, this X, capital X, F, is the cumulative distribution function of F, and capital U is the cumulative distribution function of the uniform distribution. So, I know that X, I can make here a transformation. I know that the cumulative distribution function of X is equal to R. So, if I want to find X, because at the end of the day, what I want to find is X, I just apply the inverse of the cumulative distribution of F to the uniform distribution. Okay? So the method is as follows. I generate a sample from a uniform distribution. How do I do this? Very easy. With the Python libraries and the instruction I just showed. It's just a line of code. Then I calculate X as the inverse cumulative distribution function of my samples. And this is the way of sample, okay? Okay, this seems very easy, but it's not that easy because you have to be sure that you can calculate the inverse function of f, which is not always the case. So we are going to see some examples now. Well, this is a very easy example, but it's just to illustrate for a proof of concept. Suppose we have the linear function f of x equal to x in the interval 0, 1. Because in minus infinite, and if this cannot define, not all the sampling can be between minus infinite and x. It depends on the function. So how would you suppose, what would you suppose that is this x of R? Anyone? What is the cumulative distribution function of f? Remember, cumulative distribution function is the integral between minus infinite and x of x f of x prime dx prime, okay? But in this case, f of x is only defined in the interval 0, 1. So this is the integral between 0 and x, being x less than 1 of this. Okay, this integral is very easy. Come on. Anyone? You want to observe the course? Really? X squared. What? You still do not deserve the coffee day. So what would be? So capital F is x squared. What is the inverse function? Square. Very good. Okay, this is the answer. So how do you sample from 2x using the uniform distribution? You generate a uniform sample, and then you apply the square root to your samples. Okay? So this is the way. And okay. Here you have another example, and I'll give you maybe 2 minutes to calculate it. Yes. 2 minutes, and we go for a coffee break. I think one of the mistakes is that I put the result in the PDF. I should not do this in the future. So I give you as an exercise, and this is for your homework as well. Anyone? Anyone wants to come here and solve it? That's the best coffee. It's a beer if you go to Lima. No way. People do not drink beer anymore. Young people do not drink beer anymore. Okay. Anyone? You want to come here? Don't be shy. You can speak Spanish. Yes, yes. You can speak Spanish. You see, it's very easy, people. All of you are bachelors. So if you come so far, if you came so far, you should have solved much difficult problems, much more difficult problems.
Yes.
Speak Spanish. So first you have to calculate the cumulative distribution function. Yes, yes. I just say it in English for the non-speaking Spanish person. Okay.
La definimos de 0 a X.
Well, very good.
Listo, aprovecho la constante, le agrego un negativo.
Okay.
Y la parte que le entendí es que hay que despejar.
Hay que estoy verde.
Bueno, yo lo estaba haciendo así. Aplico logaritmo a ambos lados.
Very good.
Me baja esto y esta X sería el X de R. Sería logaritmo de 1 menos. Y aquí, en vez del F, creo que le colocó el F, ¿cierto?
Perfect. Invented this problem. Okay. So, how do you sample from this distribution? You sample a uniform distribution, and then you apply this transformation to your uniform distribution. Okay? You can do it for any value. After the break, we will see how you can sample from a bivariate Gaussian distribution. Because these are unidimensional distributions. But usually we have multidimensional distributions, and there is a very nice explanation of how you sample from a bivariate distribution, even though in practice you will be performing this from the library, okay? Because this can be done from the library. But my idea is to give some flavor, because I think if you conceptually understand this, you will be able to perform this for more complicated functions. Okay? And I think there are not exercises for this. There are exercises that you have to make for your homework that are related to the importance sampling. Okay? To calculate, there is one exercise to calculate it with naive Monte Carlo, that is without importance sampling, and there is another exercise to calculate it with importance sampling. Okay? So now we can go to the code. Ahora se encuentra, bueno, tampoco se vuelven con todo una cosa chiquitita y mañana todo el mundo sabe.
Oh,
Ay,
is
sí,
everything okay?
yeah,
In the same place.
yeah.
So how are things? Everything's okay?
Everything okay. How
Very
about
good.
you?
Good. Yeah, just arrived yesterday night.
Okay.
So I renormalized a bit and now we're ready.
So what's your plan?
Very nice. Long, but very nice.
Yes, of course, not directly.
Not that I went to Madrid and to Santiago.
Okay.
So 40 hours in total.
Oh my God. Are you still
No, no, it's okay. Come to Tarapacá is always quite nice. Good. But please.
Let's have a coffee. Yes. Okay. Well, this last part of the class will be very short. I encourage you to do the notebook number 2 because maybe the first days the notebooks were easy, but today we have a notebook and tomorrow we will have another one. So if you don't do the notebook today, you will have a lot of homework when I go for Arica and you're not going to have anyone to consult. So, okay. Before I showed how to sample from a distribution that is not coded in any library by making a transformation from samples that were performed were taken from a uniform distribution. And now I am going to show how you can sample from a bivariate Gaussian distribution. This Gaussian distribution has no covariance, has no deviation. So mu here is, this is what we call, what you will see in statistical groups as normal sentence 0 with a standard deviation of 1 in the two-dimensional space. So this is the expression for that function. And in order to sample this, first we will make a change of variables to polar coordinates, to which you are very used to. The determinant of this transformation is also known by you. And so I have this new, so this distribution can be turned in this distribution. The algebra is very easy, therefore I leave it for yourselves. And now I can define the marginal distribution. So I define a G of rho which is integrating the two-dimensional distribution in theta between 0 and 2 pi. And if I do this, the algebra is, here I'm just integrating in theta, so I get this one. And for the marginal distribution of theta, here I have to integrate between 0 and, there is a problem here. Here I have to integrate between 0 and rho, okay? Because I'm integrating in rho, not in theta, but it's a typo just in the PDF that I will correct for the final version. So you have your marginal distributions. And now I will do the same trick I used for the one-dimensional distributions for the two marginal distributions that I obtained from the two-dimensional distribution, okay? This is nothing different from that. So I will say again that, so what I'm doing here, again, is the following. Remember, the idea behind this is the same that we did before the break, that is that the integral between minus infinity and x of f of x prime dx prime is equal to the integral between minus infinity and r of the uniform distribution of r prime dr prime, which is r, okay? But I'm doing this twice, each for for each one-dimensional distribution. So I integrate this distribution between 0 and rho. I obtain this between rho and 0. I evaluate, and this is equal to R1, because I will be sampling two times from the uniform distribution, okay? So R1 will be the samples from the first uniform distribution. And then applying the inverse function, I found rho as a function of the samples of the uniform distribution. And now I make the same trick to the variable theta, which is very easy. I integrate between 0 and theta, 1 over 2 pi, and this is equal to R2, where R2 are the samples of the second uniform distribution, or are samples that I take totally independently from R1, okay? And making the appropriate algebra, x and y will be the samples of my bivariate Gaussian distribution that I obtain applying these transformations to R1 and R2 that are independent samples from the uniform distribution. So, recalling the idea of this last part of the class, which is, I apologize, a little bit technical, is this is just a summary of how I generate a distribution, any distribution from a uniform distribution. Of course, you cannot do this with any function, because in some cases, if your function does not admit the inverse function, you are done. You cannot do it, okay? So this is for a general distribution, but you have to be sure that your distribution, your cumulative distribution admits an inverse functions. So what you do is convert f of x into a probability distribution. This is why what our fellow did before the break. You have to normalize this distribution, and then you can calculate x applying the inverse function. Okay, and I'm spoiling the class of today, of tomorrow. So that's it for today. I highly recommend that you begin to make exercises, notebooks, and so on. Remember, for approving this course, you may do the exercise that were not solved in class, do the exercise in the notebook, and implement a Markov chain Monte Carlo for a model of your interest. If you have a particular model, like Giovanni said, for example, a scalar field, or something that needs numerical integration, you're very welcome to do it, and if you want some help, I can provide it. So thank you very much, and I see you tomorrow.
Question. Aquí hay una consulta de Johan.
¿Qué?
Dice, ¿las tareas se enviarán por el mismo GitHub o...?
Sí, los notebooks, the notebooks are all in the GitHub, and the exercises are those that are not solved in the PDFs. It's easy to see. There is, I think, 1 or 2 exercises in class 1, 1 or 2 in class 2, and no exercise today. So it's easy. But he should have the notebooks. The notebooks, I put them today very early in the GitHub.
Okay, good. Okay. Okay. Any question? Okay. Okay. Thank you very much. Ahora tenemos la periodista, va a hacer una entrevista aquí en este intermedio.
Sí,
Podemos, no sé, continuamos nosotros, usted hace la entrevista a ella, ¿sería? Ya, está bien.
bueno, voy a cerrar la computadora, ¿cierto? Y...
Está bien.
Gracias.
No, está bien, pero...
Puedo cerrar el Zoom, ¿no?
Sí, eso, creo que sí, lo puedes hacer.
Sí, bien, gracias.
Okay, hello? Hello? It's good, no? Okay. Okay. Then we are going to start, okay? Professor Dr. Emmanuel Saridakis is a research director at the Institute for Astronomy, Astrophysics, Space Application, and Remote Sensing of the National Observatory of Athens, and a visiting professor at the University of Science and Technology of China. He obtained his PhD in cosmology from University of Athens, Greece. Okay, he has many publications in the area of cosmology and gravitation. Okay, his main research interests include cosmology, general relativity, modified gravity, dark energy, and observational data analysis. Okay, and then thank you very much, Professor, for the year. And then you are the host.
Thank you very much. Good morning, everyone. I would like to thank Giovanni, of course, for this nice invitation. It's always a pleasure to be here to give this talk. So we are going to discuss about gravity and cosmology, how we are playing the game of cosmology. So first of all, let me ask, how many of you are PhD students? Okay, and how many are master students? Okay, but you are familiar with the basics of gravity and cosmology, right? But I mean, even if you don't, that's why we're here. But please feel free to ask me things as we move forward. So let me spend first, how do I close this? There were people that wanted to join. And I need, I'm the, but let me, no, I need to admit, this one and this one. Yeah. I think now we're okay. We're okay, right? Okay, so these are some bibliographical things. This is a book that we wrote on the basics of gravity and cosmology and some well-known papers. I mean, I can give you the slides after the... let me admit this guy also. Okay, so he is going to let them in. Oops. Yeah. Okay, so let us start. The idea is the following, that gravity, of course, is the most interesting interaction in nature, but the one that we know less things about it. And of course, in order to determine gravity, I mean, you cannot study gravity in the accelerators because gravity is so weak. That's why we're using cosmology. In a sense, the universe is the lab to describe gravity. So first, let me just start from the basics, how we are doing physics, right? So Thales was the first guy that he invented the word physics from nature, and he said that we need to do research without superstition, religion, myth, but only with observations, experiments, and rational thinking. Now, then we come to Pythagoras. How can I move this? Okay, no, this thing. Pythagoras was the guy first invented the word mathematics, and he said that the word of nature is written in mathematical language. So if you want to do physics, we need to know mathematics, right? So get ready for that. And of course, we come to Euclid. Euclid was the first guy to understand the concept of proof. So in physics and mathematics, we need to prove things, right? We start from some axioms, then we're doing the lemmas, the theorems, and we prove. So have this in mind when we are doing gravity and cosmology. So let us start. The first concrete gravitational model were the Aristotelian Ptolemaic gravitational and cosmological model, of course, completed by many other Greek mathematicians and physicists. The Earth is the center of the universe. Heavier bodies fall faster than the slower bodies. And this model, so the Earth itself is made from 4 elements: earth, fire, water, and land. And the skies are made from the 5th element, the 5th essence, the quintessence. Remember this work? This was a very successful cosmological model in agreement with all observations until in the Middle Ages, detailed observations from the Arab and Persian school, and also in China and India, started putting into questions the details of the Aristotelian Ptolemaic model. Then we are coming to Copernicus, and we have the idea of heliocentrism. And then, of course, we have the detailed observations of Bracher and Kepler that spent 30 years of their lives in order to describe the motions of the planets. At the same year, we have the first experiments on gravity by Galileo, right? So think of that. Galileo was the first guy 2,000 years after Aristotle that decided to do an experiment in gravity. So for 1,000 years, people believed Aristotle's idea that heavier bodies fall faster. And Galileo was the first guy to make the experiment and show that no, all bodies fall with the same speed. This is interesting. And then we are coming to Newton. Now, Newton put together the observations of Bracher and Kepler and the experiments of Galileo and built the first concrete mathematical theory of gravity. So for the first time, we understood that it's the same force that makes apples falling on Earth and planets moving around the sun, the force of gravity. And for the first time, we understand that if we want to do astronomy, so to understand the laws of the stars and the planets, we need to have a theory of gravity, because gravity is the director of the universe evolution. So Newtonian gravity was a perfect theory in perfect agreement with observations until 1859, when the advance of technology allow us to do more precise observations, and we found these anomalies in the perihelion of Mercury. It was 43 arc seconds per century, but people were capable of doing so detailed measurements. And these detailed measurements put Newtonian gravity in tensions with observations, right? And of course, at 1887, we had the Michelson-Morley experiment. With the measuring of the speed of light, right? And we learn in the books that, of course, the solution to the Mercury's perihelion anomaly and to the Michelson-Morley experiment was the theory of relativity. Okay? This is what we all know. And of course, according to the theory of relativity, gravity is not a force anymore. It has been geometrized, right? So, according to Wheeler's book, in theory of relativity, matters tell space-time how to move, and the curved space-time tells matter how to move, right? So, matter curves space-time, and space-time tells matter how to move. Okay? So, gravity has been geometrized. However, you need to remember the following thing. It took 60 years to solve the tensions between Newtonian gravity and the new observational data. So 60 years, 2 generations of physicists lived in the years of tension. In the years where Newtonian gravity, which was a perfect theory of gravity, had predictions not in agreement with the new data, right? So the solution is not immediate. And actually, okay, now I'm doing the spoiler. This is what I will talk tomorrow. So, how physicists try to explain the anomalies in the Mercury's motion? The majority of them believe that Newtonian gravity was correct, but there was an extra planet, a planet between the Sun and the Mercury, called the Vulcan. So a planet that we had not seen, in a sense, a dark planet, that in the framework of Newtonian gravity was causing the anomalies in the Mercury's motion. But the answer was not a dark planet. The answer was modified gravity, general relativity. And just to let you know, even before Einstein, people tried to modify gravity in unsuccessful ways. They tried to modify the Newton's law. The inverse cube law was proposed. Extended inverse square law. All the good physicists that you know tried to build a theory of gravity. Kelvin, with his theory of everything. Lorentz, the Lorentz that we know, he tried to analyze gravity using his ether theory. Nostrom, of course, had 2 theories of gravity. And even Einstein, before general relativity, Einstein tried to find a scalar theory of gravity, which was wrong, of course. And he found the tensor theory of gravity, general relativity. And this is the theory of gravity that we have up to now, general relativity, right? So this is the action of the theory. This is the curvature scalar, and this is the matter Lagrangian. These are the field equations that you obtain from variations of the metric. And this is the source, the energy momentum tensor. Okay? But remember, now we learn this is cool, but it took 60 years for this theory to be built. And during these 60 years, people tried many, many other unsuccessful things. Okay? Just to remind you what is the situation today in gravity and cosmology. So let us start with the basics. And I think you are all familiar with that. So first of all, since in GR, in general relativity, gravity has been geometrized, we need to know geometry, right? So we have, first of all, the concept of reference frames, okay? This is important. And in the beginning, Einstein said that all physical laws should be the same in inertial frames, right? But then, with general relativity, we had the concept of general covariance. So, physics should be the same in every reference frame, okay? Now, another concept that is crucial in general relativity is the concept of equivalence principle. You know, what we call mass has 2 completely independent properties. The first is that mass has the property to contradict the change of its motion. It has inertia, right? So we should call this inertial mass. And the other property of mass is the property that masses attract other masses, right? This we could call gravitational mass. Remember that the fact that we use the same word, mass, for these two things is stupidity, right? These are completely different things. And the fact that we use the same word for that put the whole humanity into confusion for thousands of years, until in the 20th century, Einstein understood that we have to do with two different properties. Let's call it inertial mass and gravitational mass. Now, in general relativity, you assume that their ratio is 1. So you assume that it's equivalent, right? In physics terms, it means that acceleration is equivalent with gravity. Remember, the inertial mass, it's entering into the Newton law, right? So this guy here is the inertial mass, while in the attraction law, these things are gravitational mass. This and these are not the same, right? But in general relativity, we assume that they are equivalent. So this is embedded in general relativity. That's at the local terms, right? It means that gravity and acceleration are equivalent locally, not in the global sense. Now, this is very important, according to Einstein. So how we have a map between physics and geometry, right? So here in physics, of course, we have events, right? So the where and when of events. So in geometry, these are points in a topological space, right? The set of all events in physics is a continuous space. So we are saying in geometry that space-time is a differentiable manifold, okay? Now, gravitational phenomena are manifestations of geometry. So in terms of geometry means that the gravitational field is the metric. The metric of the space-time is the gravitational field. It describes the gravitational fields. Now, point-like particles move in space-time, follow the world lines. So how a free particle is moving. And in general relativity, we are using the concept of geodesics. And we are calling them straight lines. And the laws of physics are the same for all observers, of course. We are saying that general relativity should respect general covariance or diffeomorphism invariance, okay? Now, I guess you are familiar with all this stuff. So we have a manifold, and we supply that with a metric. And of course, you know that if we have some space, we can define the tangent space on that locally. And apart from the metric, we have the concept of parallel transportation, which is connected with the concept of connection of space-time. So Einstein says in his book that he was sitting in his office and he realized that motion in physics means that the space-time has a connection. A connection is the rule that connects two space-time points. How I will move from one point to the other? Equivalently, if I have a vector, how can I parallel transport this vector? I need a rule. This is independent of the way you defined your metric, right? So the ancient Greeks had discovered two concepts. The metric, from the Greek word to measure, is the rule that helps you to measure things, angles, and areas on your manifold, right? But the concept of connection of what is parallel is independent of the metric. Remember that, because there is a confusion. I will tell you, there is an accident, not confusion. So I need a rule how to move my vectors. I need a rule for parallel transportation, and I need a connection, right? So in general, with flat and curved space-time, if I parallel transport a vector, so here, this is a flat space. If I do a parallelogram, my vector comes back in the same space. If my space-time has curvature, then the parallel transportation of the vector will come in the initial point with an angle, and this angle quantifies the curvature. Do you agree with that? Okay. But remember, curvature is a property of the connection, not of the space-time. And I will tell you a similar thing is that in general relativity, points follow geodesics. And we are saying that these geodesics are the straight lines, right? So if I am to Arica and I want to go to London, then the geodesic is to go, alongside the curvature of the Earth, right? If you see it from above, it seems not straight, but these are the straight lines. Okay, and in this way, you are all familiar with the Levi-Civita connection. So in general relativity, we are using the Levi-Civita connection, right? So this is the equation, the geodesic equation, the motion of a free particle. And just let me give you the expression of the Christoffel symbols in terms of the metric, the derivatives of the metric. You are all familiar with this expression, right? Okay. Be careful here. This is the connection, and I can express it with a metric. But before I told you that the connection is independent from the metric. So what's going on here? This is an accident of general relativity. So only in general relativity, only if I use the Levi-Civita connection, I can express the connection in terms of the metric. And this brings another confusion. The geodesics and the straight lines do not coincide in general. They coincide in general relativity. A geodesic and the straight line is the same. So you can use the same words interchangeably. But in more complicated geometries, geodesics are the shortest lines between 2 points, and the straightest lines are the more straight lines. We call them autoparallel curves. Autoparallel means that the curve has very, very small deviations from the tangent. So you see, these are confusions that we are making in general relativity. The connection seems to depend on the metric. This happens only for the Levi-Civita connection, only for general relativity. And also that the geodesics are the straight lines. Again, this happens only for general relativity. So what is the equation of a free particle? In standard flat space-time, just it has zero acceleration. In Newtonian gravity, if I have a gravitational field, then the acceleration is connected with the force. And for a general metric, in general relativity, this is the geodesic equation. So the particle moves alongside the geodesics, which are determined by that, okay? And of course, you know how to find these equations by extremizing the proper time along a timeline. So these are very easy things. You take one particle, you draw a time-like word line between 2 points, and you extremize this guy. If you are doing that, you obtain, this is a very simple exercise. You obtain the geodesic equation here. Okay? So let me proceed now. Historically, how Einstein found the field equations. First, he said, okay, I will connect gravity with matter distribution. Okay. Let us describe matter first, which is easier. How can I describe matter? I need a 4 times 4 tensor, and the 0, 0 point will describe the energy density. And then I will have all the motions and the momentums and everything. So I have a symmetric 4x4 matrix. This will be on the right-hand side of the field equations. Okay. So on the left-hand side, I need a geometrical object, which must be also a 4x4 symmetric tensor in order to equate with that. And he built what we now call the Einstein tensor, right? This is the only geometrical thing that you can build. So Einstein found the field equations first, without knowing the action. And then he tried to find the action. And he spent many years, and actually Hilbert was the one to give him the final boost, that these equations are coming from variation on the Einstein-Hilbert action. And that's why we call this action, they published with three days different, we call this action Einstein-Hilbert action. So you see, Einstein first found the equations, and then he was trying to see from which action these equations are coming from, and he found the Einstein-Hilbert action. Now, I know that Susanna put you some things for tomorrow, but I want, of course, if you know, you know. But if you don't know, I want everyone to be able to perform variation in the Einstein-Hilbert action to find the Einstein field equations. Do you know this? All of you? No, eh? So you have 24 hours to do this calculation. Yeah, come on, this is very easy. I mean, if you have the properties, what is the Ricci scalar comes from contractions of the Ricci tensor and then from the Riemann tensor. So you go from here to here, then you break it, and you have three terms, and you perform variation of these three terms. And of course, you are using the properties of the Ricci tensor and the Riemann tensor in terms of the connection, right? And you are playing with the connections. This is an easy calculation, and you perform some partial variations. And of course, you need to do some simple things, how the metric and its determinant are connected in order to take this kind of variations. So those that know it, explain to the others how to do that in order to be able tomorrow to do this variation. So the variation of the Einstein-Hilbert action gives you this thing, and then you just put it and you find the Einstein field equations. So we now know which Lagrangian gives rise to these field equations. But remember that historically, Einstein first wrote these equations, and then he tried to go backwards to solve, to find the Lagrangian. So this is general relativity. Okay? So any questions up to now? Very good. Now, general relativity has some predictions. The first thing is that this is also a very easy exercise that you can find in textbook, that in general relativity, if you calculate the motion of one body around one other body, then you have, this motion of the perihelion, right? And this is the prediction. And you obtain exactly the same number as the data point. Another prediction is the bending of light, of course. So light bends as it passes through heavy, massive objects. And you can find, again, this is an easy exercise, how you are going to find this bending. Okay? Now, we have our theory of gravity. So this theory of gravity determines the evolution of the universe. So now, let us start doing cosmology. Let us see how the universe behaves. Now, in order to do cosmology, we need to go from the galaxy scales and higher, right? So the galaxy scales are 100,000 light years. Now, if you go to 1 million light years, we have the group of galaxies. Groups are not so gravitationally connected objects. And then at 10 million light years, we have the clusters of galaxies. The clusters of galaxies that may have thousands of galaxies are gravitationally robust and connected quantities, objects, right? Now, if you go to 10 to the 8 light years, we have the concept of superclusters of galaxies. So clusters of galaxies. So a supercluster can have hundreds of clusters, and each cluster can have thousands of galaxies. And if you go at 1 billion light years and higher, the universe becomes homogeneous and isotropic. And now we start doing cosmology. So we don't care about the details at smaller scales. Of course, our solar system is not homogeneous and isotropic. But you can see a map of the universe there. The universe itself is homogeneous and isotropic. And this is the starting point for cosmology. It is the so-called cosmological principle. By the way, this is an axiom. It's an indirect result. We have not traveled in the whole universe to show that the universe is homogeneous and isotropic. Actually, what we have is we have only one observational point, Earth. All our observations are made from Earth or from the solar system, let's say. So, according to observations, the universe is isotropic because all directions are the same. But we don't know if it's homogeneous. Now, suppose that the universe is not homogeneous. Suppose that we have a non-homogeneous system. A non-homogeneous system can have at most one isotropic observation point. So, suppose that we have a flat city, and the city has a hill, so it's not homogeneous. Every observation point will be anisotropic because at every point, if you're scanning, you will see the hill. So you understand that you are not in an isotropic observation point. But there is one isotropic observation point, and this is the top of the hill. So if you are on the top of the hill, you will see that the city is isotropic. So if the universe is not homogeneous, since Earth is an isotropic observation point, it means that either the Earth is the only isotropic observation point in an inhomogeneous universe, so we are the center of the universe, or every point is isotropic observation point, so the universe is homogeneous, right? So that's why we call it an indirect result, and we are living in a homogeneous and isotropic universe. Very good. Now, observations. What this guy, the best basketball player in the University of Chicago, described, Hubble, he saw that all galaxies move away from us, right? And actually, the further they are, the faster they move. How we are measuring speeds in cosmology? Through the Doppler effect, right? You are all familiar with that. And this H naught today, this ratio here, is the Hubble function, 70 kilometers per second per megaparsec, right? Is how fast the universe expands, right? You are all familiar with the Doppler effect. Now these are from school. So we get a redshift in the radiation of a moving source. A redshift means that the source is moving away from us, okay? And you can see that, now you can see that, okay, if every galaxy moves away from the Earth is the center of the universe. No, because it's not that all galaxies move away from us. All galaxies move away from all galaxies. It means that the universe itself expands, the space-time expands, right? So take an olive bread and you put it in the oven and it expands. So this reference olive sees all the other references, all the other olives to move away from it. But this is true for every reference olive. So everything gets away from everything. This is that the universe expands. Okay, but since the universe expands, what will happen if we go backwards in time? It means that everything that we see, we're in a less distance and less distance and less distance. And if you put down the numbers, 14 billion years ago, everything that we see all these galaxies and superclusters of galaxies and everything, was concentrated in super dense and super hot point that went through a big bang. And actually, this is the Big Bang theory, and you can easily calculate the age of the observable universe. Now, remember Euclid, we need to prove that. Okay, this is a nice theory. How we can prove it? You need to see what are the predictions of the theory. Now, prediction number one, if this happened, if the Big Bang has happened, then at the very early fractions of second and the first seconds of the universe after the Big Bang, the temperature was very high, 1 billion kelvins. So you have nuclear reactions, and you had the primordial nucleosynthesis. So hydrogen gave helium and lithium in the first elements. So if you put down the numbers, the abundance of these light elements in the universe proves that this happens. So the helium and lithium are not created only in stars, right? Only 4% of that has been created in stars. The other is coming from the primordial universe. Now, prediction number two. In the primordial universe, of course, we have all these nuclear reactions, and we have the creation. So if you have neutron and proton, you have the creation of gamma rays, of high energy photons, okay, with this wavelength. Now, the universe expands, of course. So the wavelengths of the photons expands. So it means that they lose energy, right? So around 380,000 years after the Big Bang, the temperature of this black body radiation of the photons had decreased to 3,000 kelvins. So from this moment and later, the photons do not have the energy to ionize the hydrogen atoms. So before that moment, if you had a proton and an electron coupling together forming a hydrogen atom, then a high energetic photon will come and destroy that atom completely because it had the subsequent, the required energy. But after this point, on average, the photons do not have the energy to destroy the hydrogen atoms. So hydrogen atoms are formed and photons are starting to propagate freely. And the universe becomes transparent. Of course, the universe continues to expand. So if you make the calculations, today, if the Big Bang has happened, today, we should have photons all around with an average temperature of 2.7 Kelvin degrees. So if Big Bang has happened, the prediction of the theory is that if you are on Earth, at any direction that you look, we should get microwaves because the photons of this temperature, they correspond to microwaves. Indeed, in 1965, Penzance and Wilson completely randomly, they had an antenna to measure some other things, and they saw that indeed from any direction you observe microwaves. And of course, they got also the Nobel Prize, although they were completely, like in the beginning, they thought that this was an error from the pigeon drops. So the pigeons had destroyed the antennas, and they put their PhD students like you to clean the antenna every day. But of course, in the end, they had to accept that it's not that. It was a measurement. Okay. Now, of course, the Big Bang solves many problems. For instance, why the sky is not bright. If the universe is infinite and static, then in infinite stars, the sky will be bright. Or why the radio galaxies densities increase with redshifts. Because if you are in higher redshift, you are more in the past. So more in the past, the universe was smaller, so the density was higher. But it has, after these successes, it has some theoretical problems, right? The first is the horizon problem, of course. Why the universe is the same everywhere? Because if I look very, very far away that way, very, very far away that way, these two regions never had the time to interact. So why they have the same properties? Why the electron mass is the same in the universe, in these regions? the flatness problems, of course, why the universe is spatially flat. By the way, the universe seems to be spatially flat. The three-dimensional curvature is zero, not the four-dimensional. Of course, in the four dimensions, the universe is not flat. This is the definition of general relativity is curved. It's spatially flat. And of course, the monopole problem, you know that the grand unified theories predict the existence of magnetic monopoles. These are related with the quantization of charge. But these do not exist. We have not observed any of this, right? And that's why the Big Bang theory had to go through a lifting in the early 80s, and we put the phase of inflation. So according to inflation mechanism, during the very, very early stages of the universe, 10 to the minus 36 seconds after the Big Bang, through some unknown mechanism, the universe went through an exponential expansion. And although this phase lasts very, very short interval, it increases the size of the universe 10 to the 30 times, right? So this mechanism solves all the problems. First of all, our observable universe is just one tiny part of the whole universe, which may be infinite. So all our universe comes from a causally connected region. Now, due to the huge expansion, the spatial curvature becomes almost zero. It's similar to the point that the Earth seems to be flat because it's very, very big. It's not flat, by the way. So that's why you solve the flatness problem. And of course, due to the huge expansion, the monopoles have been expanding the whole universe. So statistically, in our observable universe, there is only one. That's why we have not seen that. So you solve all these problems with the theory of inflation. So one causally connected region gave us the whole observable universe. Okay, and if you want to see it, to sketch it, so this is without inflation. This is the universe. You see, these are three disconnected areas, so they have different properties. Now, if there was not inflation, today our observable universe could see these three parts. So if I could see very, very far away that way and that way, I could see completely different regions of the universe, which is not the case. But if inflation happens, then the whole universe expanded astronomically, and our observable universe is just within this causally connected region. So the whole universe has the same properties. Okay? Okay, this is a bit more mathematical. So in order to solve these issues, we need what we say the comoving horizon to decrease at one point. So this is time, this is the comoving horizon, decreases, and when inflation ends, it increases again. So we are inside a causally connected region. Now, observations continuing 20 years ago, we found that the universe acceleration is, the universe expansion is accelerated. It becomes faster and faster. How we did that initially with the supernova. So Permuter, Smith, and Rees observed 50 supernovas, and they found that the supernovas were less bright than expected. Less bright than expected means that the universe expands faster today than in the past. So light travel more time than expected. So the universe expansion is accelerated, right? By the way, the supernovas in cosmology are very important points, objects, because we call it standard candles, because we know their physics. Remember, in cosmology, we can easily calculate speeds through the Doppler effect. It's very easy. But how can we calculate distances? This is very hard, right? Of course, you cannot see a galaxy moving so fast that it becomes smaller and smaller during our lifetime. So how we can measure distances? If you know the physics of an object, then you can do that. For instance, if I can see a light, that light over there, if I know how light it emits, and if I know how light what the amount of light I observe here by the inverse square law, I can find the distance, right? The issue is that in cosmology, you don't know the physics of the object, but there are some objects like the supernova that you know exactly how much light they emit. So you see how much light it comes to you, and you can calculate the distance, right? And this is what dark energy is. So we now know that 70% of the whole universe concept is this unknown form of dark energy. Why we call it dark? Because it does not interact with electromagnetism. So we cannot see it. And of course, the possible explanation is the cosmological constant. What Einstein says it was the greatest blunder of its life. Okay? And another observation has to do with the existence of dark matter. Now, we have two observations. The first is the galaxy rotation curves. So if you have a galaxy that it rotates around its axis, right? So the mechanics of the rotation is determined by the mass of the galaxy. These are simple things that we learn in school. Now, the problem is that the speeds of the rotation, so the rotation curves, are not in agreement with the mass of the galaxy. It seems that there is more mass there that we cannot see. And the second experiment is if you have the collision of clusters of galaxies, again, the mechanics of the collision is determined by the mass of the momentum conservation and everything. So you could calculate the speeds by the mass. But the problem is that the mechanics of the collision is not in agreement with the mass that we have there. So if you put both these observations together, we conclude that 80% of the matter is non-visible. It is an unknown form of matter that we call dark matter. Why dark? Because it does not interact with electromagnetism. Okay? So, and what we see, the distribution of galaxies in the universe is actually the distribution of this dark matter. Now, another observation. We said in the beginning that according to the Big Bang prediction, we should get an isotropic distribution of microwave radiation in its direction with temperature 2.7 kelvins. This is what we observe. So, a completely isotropic distribution. But if you start seeing this in more details, you can see some small anisotropies up to 10 to the minus 3 level. So you have colder and more hot directions. So there are deviations. These are the Kobe satellite results. And then we have the WMAP results. You can see the increase at the accuracy level. And then we had more latest, the Planck results. So you can see here clearly a structure. So at first order, of course, this is a completely isotropic distribution. But to the level of 10 to the minus 3, 10 to the minus 4, we have small anisotropies. How can I extract information from here? I calculate, of course, the spectrum. So this is the spectrum, the correlation of 2 points within this thing. And indeed, you can see here a structure. So the CMB radiation spectrum carries information. And this information gives us very, very important numbers. First of all, the first peak is consistent with zero special curvature. This is how we know that the universe is spatially flat. And then the other peaks gives you the baryonic matter energy density, the third peak, the dark matter energy density. This is how we are measuring that. When we say that 25% is dark matter and 5% baryonic matter, how do we know that? From here, right? And of course, this is in agreement with the large scale structure. So let me give you another argument in favor of inflation. So inflation solves all this, the horizon monopole and the other problems. But apart from that, inflation gives you the initial seeds, so the quantum fluctuations of this inflaton field gives you small anisotropies and inhomogeneities, which were the initial seeds after you had the large-scale structure, right? So you need inflation in order to create you also the CMBs anisotropies. This, how these were created at first place. Who broke completely isotrope homogeneity? The quantum fluctuations of the inflaton field. This gives you the initial seeds, and after the years passed, you had this embedded in the CMB radiation and also in the large-scale structure. Okay? So this is very important. And of course, another more qualitative argument about inflation is the following. Of course, you know Amerigo Vespucci. So he was the first guy that came to South America. And he first saw the delta of the Amazon River. He just explored 40, 50 kilometers of that. But because he found this structure, he was clever enough to think that in order for this structure to have been created, I need to have a huge continent here, not only a small island. He never saw that. He realized that in order for this structure that I can see here to be able to be built, then here I have a huge continent that took, of course, his name in the end of the day. The same happens with the universe. Because the universe has the properties that it has, we conclude that the observable universe, not only it's not the whole universe, is a very tiny, tiny part of the whole universe that can be infinite. Okay? So there are infinite bubbles, and our observable universe is one of them. Okay? So this is a summary of observations that we have up to now. The Big Bang. So that's why we're saying that the Big Bang is a bang, actually. It's the history of our observable universe. You don't know what happened to the other regions. We are not metaphysicals. Our universe came from the Big Bang. What happened before here or outside this, it's something that we will never know. So, Big Bang, inflation, radiation era, matter era, dark energy accelerated era, inflation, and this is the composition of the cosmos. So 0.03% are the heavy elements like us and the Earth. 0.3% are the neutrinos, 0.5% are the stars, only 0.5% are the stars, and 4% are free hydrogen and helium. So this 5% is what we know. The remaining 95% is what we don't know. And actually, it is 25% of dark matter and 70% dark energy. Do I need to do a break? Are there any questions up to now? I mean, you told me to finish at 2 o'clock, but do you want to do a break of 4.5 minutes? Okay, 4 minutes break. Okay, so let us proceed. I have a nice question from Juan Gustavo in the chat about the connection and how it is related with the properties. We will answer that in detail tomorrow, because tomorrow we are going to enter the modified geometries and modified gravities, where all these play a role. So for the moment, we are using the simple standard Levi-Civita connection, and everything is fine. So we have the observations, and we have the gravitational theory. How are we describing the universe? How we are doing cosmology? These are the very basic things. So we need to describe a four-dimensional universe. So, first of all, we need to define our metric. Okay. We need to define our metric. According to the cosmological principle, we are living in a homogeneous and isotropic universe. So from the metric tensor is 4 by 4. It has 16 functions. Because it should be symmetric, it has only 10. So from these 10, if you apply the symmetry of homogeneity and isotropy, you have only one unknown function, the scale factor. So this is the metric consistent with the symmetries of isotropy and homogeneity. So this is in spherical coordinates. This k here has to do with the spatial curvature, is 0, +1 or -1 for flat, closed, on open or open three-dimensional geometry. So this is our starting point to do cosmology. These are the field equations. This is the action of general relativity, and from variations of that, you get the field equation. This is the exercise that I ask you to do for tomorrow, those that you don't know. So how from this guy, you get the Einstein field equation. Now, I have the Einstein field equations, G mu nu equals T mu nu. I plug as the metric the isotropic and homogeneous metric, the so-called Friedmann-Robertson-Walker metric. So I have this metric. I calculate gamma 0, 0, 0, gamma 0, 0, 1, all the Christoffel symbols, all the Riemann tensor coefficients, the Ricci tensor, the Ricci scalar, and the general field equations gives rise to the two Friedmann equations, the 0, 0 equation and the other three. You are all familiar with that, right? So if I have the general Einstein field equations, plug in the FRW metric, and I obtain the Friedmann equations, you can clearly see now H is A dot over A, is how fast the universe expands. You can clearly see now the essence of general relativity, right? So on the left-hand side, you have geometry, and on the right-hand side, you have the matter distribution. And remember, because we are at large scales, the universe is homogeneous and isotropic, so matter is completely homogeneous, and all that counts is the energy, density, and pressure. So I assume that matter is determined by a perfect fluid. Okay? So I don't care about the solar system and the galaxy scales. If I see the whole universe in total, then it's a fluid, and each particle of the fluid is a galaxy or a cluster of galaxies. So I don't care about the microphysics. And of course, since matter is conserved, this is the conservation equation of the matter perfect fluid. Now, I need an external input, and this has to do with the equation of state of the matter fluid. This has nothing to do with gravity. It's a property of matter. So the equation of state is P over rho. And this is how you are doing simple calculations. You take the conservation equation, you solve it. So this is the evolution of the energy density of your matter. And then you plug this guy to the Friedmann equation, and you solve it, and you find the scale factor of the universe. I solve the universe. This is what I need to do to find how fast the universe expands. So if you have a matter universe, it means that W is 0, matter is dust. Then here, this is 0. And then for matter universe, the evolution of the scale factor is proportional to T to the 2/3. For a radiation universe, where W is equal to 1/3, you find this, and then this, it proves that in a radiation domination universe is proportional to the scale factor to square root of T. Okay? This is, of course, if you have one fluid in the universe. If you have a second fluid and you have two fluids simultaneous, then it's more complicated to solve the equation. So, in general, This is the standard model of cosmology. The Lambda CDM concordance model. We have a universe. In the beginning, we have the inflationary states, and then we have radiation, matter, and cosmological constant. This is the first Friedmann equation, and this is the second Friedmann equation. You see the three fluids here. And of course, the equation of state of the cosmological constant is equal to -1. So this model is perfect. It describes the thermal history of the universe at the background level. So the sequence of the matter, radiation, and dark energy era. And all the epochs. Now, let us come back to the CMB spectrum. So I told you that this has some peaks, and from these peaks, we understand that the spatial curvature is 0, and the matter and baryonic matter and dark matter energy densities. Why is that? Because this spectrum is sensitive to these quantities. You see, if I do simulations and I'm changing the spatial curvature of the universe, you see the first peak moves. So by making a fit to the data, I find that omega kappa is 0. And you see, omega lambda, if you play with omega lambda, this tail here moves up and down. So by fitting the data, I find that omega lambda is 70%. And again, for baryons and dark matter, you can see how the peaks change. So you see, I make a fit here, and the data tells me what are the numbers. Okay, good. Large-scale structure. I don't have time to go all this in the details, but I will tell you that, okay, at the background level, the universe is completely homogeneous and isotropic. Okay. But if I start zooming in, I can see some small deviations from homogeneity and isotropy. The real universe is not completely homogeneous, right? There is a large-scale structure of the galaxies. I have galaxies here and there, and voids of galaxies here and there. I need to explain that. Why the universe has this large-scale structure. And of course, you start with the primordial initial conditions, the quantum fluctuations, and if you do your simulations, you observe that the universe clusters, and you have a distribution of galaxies. Now, the way that this is happening has to do with the theory of gravity and the matter distribution. So this is the spectrum of matter large-scale structure that we have. So we need to explain that. Why the universe, the matter is distributed that way, and this is what we're doing in perturbation theory. Now, in principle, we will need many hours of doing the perturbation theory in cosmology. If you are doing a PhD program, you should know it very, very good. There are many textbooks. For instance, Bauman is quite nice, or Dodelson book for this. Those that are doing master students, your master thesis, it should be good to start getting into that. So the idea is the following. I depart from homogeneity and isotropy. I'm zooming in. So I start seeing that the universe is not completely homogeneous and isotropic. It has a structure. I need to explain that. How I can do calculations. First of all, we need to perturb the metric. So abandon the idea that the metric is homogeneous and isotropic. It is at the background level, but let's put some small deviations. So there are three kinds of deviations, of perturbations that I will throw in. The scalar, vector, and tensor perturbations. Now, there is a famous property, is the scalar vector tensor decomposition theorem, that these perturbations decouple at the linear level, so I can study them independently. So I can focus on scalar perturbations separately, on vector, and separately on tensor perturbations. Tensor perturbations are the gravitational waves. Now, I will go quickly here because we don't have a lot of time. You can ask me later on, or those that knows should help the others. So let's consider this perturbation. So I make a coordinate transformation in time and space of zeta and psi. So let's focus only on scalar perturbations. So the metric is perturbed like that. Okay? Now, the idea is that if I'm doing that, so this is how the metric transforms, and I face the problem of some of these could be fictitious perturbations or real perturbations. In a sense, I face the problem of gates invariant perturbations. I need to define gates invariant quantities, of course, right? So instead of these phi and psi perturbations, I can introduce these Barden potentials. Now, I perturbed also the matter sector. I perturb my metric. I need to perturb the matter energy momentum tensor. So this is how I perturb. This is the background homogeneous thing, but these are small inhomogeneities depending on both space and time. So this is delta rho and delta p. And you continue. These are standard things. Have you done perturbation theory, for instance, in quantum mechanics, in the hadrons and atoms? It's the same idea, but it's more complicated because I have tensor things and more indices, but the idea is the same. I perturb a little bit my thing, and I need to see what's going on. So I can define some quantities, like the comoving density perturbation, or the curvature perturbation, or the comoving curvature perturbation. And this is important. Typically, from space-time, I'm going to Fourier space in order to be in the momentum space. So these are the Einstein field equations. I perturb this part, the matter part, and also the geometry part. And from this perturbation, I'm obtaining equations like that. You see this psi and phi are the perturbed quantities. These are zero at the background level, and at the linear perturbation level, these are non-zero. And I have an important equation which is called the Poisson equation, right? And I can manipulate these things. So if there is a zero anisotropic stress, then the two metric potentials are the same, this phi and psi. I can use them interchangeably. This is the perturbation of the metric, and I can now focus on the quantities that are called delta. Delta is delta rho over rho. So if the universe is homogeneous and isotropic, delta is zero. But in the real universe, is a little bit larger than zero because I have a non-zero delta rho. So delta rho over rho is this matter over density. This is the important thing that I need to find. I need an equation of delta. Why? Because delta I can measure it. If I have a distribution of galaxies, I can measure what is delta rho over rho. So I need an equation for that. So this is the perturbed metric. I need to choose my gates. For instance, in the Newtonian gates, you assume that this B and E are zero. These are the equations, the perturbed equations. And you go to momentum space. And in the end, this is the equations we were looking for. We have an equation for delta, this matter of density, the deviation from homogeneity and isotropy. So this is determined by the Hubble function. So the background evolution plays a role, of course. What happens in the background also plays a role in the perturbation. Here is the Newton's constant. Of course, gravity determines the matter clustering. So you see, you have gravity forcing matter to interact, and the expansion of the universe tends to dilute this. And of course, here it appears the sound square of my fluid. Okay? And actually, this is inside the horizon. So I'm studying the perturbations inside the horizon of the universe. So I'm focusing on scales that are much larger than the Hubble scales, the momentum scales. So in terms of length, I'm inside the horizon of the Hubble horizon. I don't care what's happening outside the Hubble horizon. Okay? And of course, if I assume that I have the matter fluid, matter has zero equation of state and zero span speed, this is a very simple Jeans equation. So you see the idea. I know that I went fast because you need many hours for that. The idea is you take the background homogeneous anisotropic universe, you perturb it, so you perturb the metric and you perturb the matter energy momentum tensor, and you connect the perturbations of matter with the perturbations of the metric. The perturbations of matter are this matter of the density, and I have an equation for that, but this I can measure. So I can measure and explain the matter clustering. Is it clear? Is there any question? But you can study all this in standard textbook. So now let me give you the results. So in order to study, we have the questions. Okay. We need to choose, first of all, what is the fluid that we look? We are interested in the matter fluid because the galaxies are made from matter. Okay. So we will focus on the matter fluid. But then we have the background level. Which determines the background level? First, we have the radiation era. So the radiation determines the universe. Then we have the matter era. Matter determines the universe. And then we have the dark energy, the cosmological constant era. So we have three eras. And we focus on the matter fluid. You could focus also on the other fluids. So the idea is the following. We are in the early universe. The universe is radiation dominated. What does it mean, radiation dominated? This is the evolution of the scale factor. We found it before, square root of t. So h is 1 over 2t. So this is the background universe, a radiation dominated universe. I am plugging this in the evolution of matter perturbations, of matter over density. This is the equation in Fourier space of delta, and this is the solution. It means that the perturbations of matter in a radiation universe are proportional to the logarithm of t. So they increase very, very slowly, practically no increase. Okay? Now, let us go to the matter-dominated universe, so after radiation. So the background is determined by matter itself, and I want to see how matter clusters. Again, this is now the background evolution. This is the equation, and this is the solution. What do you see? Matter perturbations increase proportional to t to the 2/3. So much faster than before. So here is where matter perturbations are created. The large-scale structure of the universe was created during the matter era. Okay? And just to see that, if I go now to lambda domination, so I'm in the dark energy late time acceleration. Suppose we have complete dark energy, then the universe is exponential. The scale factor is exponential. We are in a de Sitter universe. If I put this here, I found that delta is constant. So in the dark energy era, the matter perturbations are not increased anymore, but they remain constant. So what is the summary of all this? Matter perturbation, the large-scale structure of matter, was created during the matter era. Okay? And you can see that. Okay, these are in the co-moving horizon, and we are inside the perturbations. So you can clearly see now how, if I give you an initial distribution of matter, through all this procedure, how this spectrum becomes the spectrum that we observe. So we proved that in Lambda CDM scenario, apart from explaining the background evolution of the universe, inflation, radiation era, matter era, and dark energy era, at the background level, it's perfect. We can also describe the universe at the perturbation level. We perform the perturbation analysis, we found the equations for delta. Delta is the matter over density, is delta over rho. So it describes you what is the distribution of matter. And we found its evolution with time as the universe passed from radiation to matter and to dark energy region. And we saw that this is exactly the spectrum that I showed you before, right? So with this equation, you can describe this. These are the data. This is exactly what we found. Okay? So we explain the distribution of galaxies. Okay. And just now to give you an example, suppose that I make simulations. Suppose that I don't have lambda. I have only matter. Omega matter is equal to 1. This will be the evolution of perturbations. So Z in the past, Z is equal to 1. Today, you can see the evolution of the universe. And if you assume that there is lambda, so omega matter is only 0.3, this is the evolution of the universe. So if I show you this picture, you can compare it with the real universe and tell me what is the amount of lambda. This is how we found that lambda is 70%. You see? So the simulation is, of course, is affected by the cosmological quantities. So in summary, this is a perfect model, the Lambda CDM paradigm. These are the Friedmann equations. It describes the universe at the background level, and it describes the universe at the perturbative level. So at the background level now, what we are doing, we take our theory, and we predict background-related quantities, such as the Hubble function as a function of time, or as a function of redshift, it's the same, or the density parameters, omega m and omega lambda, or the equation of state parameter for the fluids. So these are background quantities, and I compare this with the data. Supernova, baryonic acoustic oscillation, CMB data, cosmic parameters, etc. And I'm in agreement with the data. And also, as I told you, I can go to perturbative level, so I depart from homogeneity and isotropy. And this is the equation of delta, the matter of the density. If the universe was completely homogeneous and isotropic, delta is 0. In the real universe, delta is not 0. I have the equation of delta. These are the scalar perturbations. This is the equation of delta. Here I can define an observable. It's called f, which is d of logarithm of delta of d of logarithm of a. And I can parameterize that. This f is omega m to the gamma, and the gamma is the growth index, right? And now I can define this observable, f sigma 8. What is this f sigma 8? Is the time-dependent root mean-square fluctuations of the density field within spheres of radius 8 megaparsecs. That's why we call it sigma 8. So I'm taking spheres of radius 8 megaparsecs, and I'm counting galaxies. And I'm counting delta rho inside there. If the universe was completely homogeneous and isotropic, it will be 0. But in the real universe, within these spheres, I have a spectrum of galaxies. So this is f sigma 8. But if you go back, I have the question. So the observed f sigma 8 is related with my theory of gravity and my cosmological model. So by fitting with the data, I can test my theories at the perturbative level. And then I could use data related to perturbations. I'm measuring galaxy distributions, and I can test my theories. So this is how we're doing cosmology. First, you check your model at the background level. If some theories cannot be in agreement with the background universe, then you kill the theories. And there's those that are successful. You are doing perturbations, and then you compare it with the perturbative related data. Okay, any questions up to now? Very good. Lambda CDM is very transparent model. However, it has some issues. Although it's extremely successful in describing the data, it has some problems. And I will tell you the problems, and then probably at 2 o'clock we need to stop. So Lambda CDM is a perfect model. It can describe the evolution of the universe at the background level and at the perturbative level, but it has some open issues. First, general relativity, which is the underlying gravitational theory, as you know, is non-renormalizable. It means that it cannot get quantized with the standard techniques that we are using to quantize electromagnetism or the other three fundamental interactions, right? The cosmological constant problem. What is this lambda? Okay, you throw it in the equations geometrically and you solve the problems. Okay, but what is its value? We are saying that this has to do with the vacuum energy. So if you calculate lambda, you obtain 120 orders of magnitude larger result. So this is the worst error in history. Nobody has done a calculation with an error of 120 orders of magnitude. Now, how to describe the primordial universe? I told you the kinematics of inflation, but we don't have a concrete inflationary model. I told you what should happen with the comoving horizon and everything, but what is the underlying mechanism? What is the physics of inflation? We don't know that. And we have some tensions with the data. I will come to that. Okay? So let us see one by one. Now, GR, if you start doing the same things that we are doing in electromagnetic, have you done a quantum field theory in the master thesis, in the master program, or not yet? But anyway, the idea is the same. If we take electromagnetism and we quantize that, very good. If you start doing the same things in general relativity, you cannot find any result. The theory cannot get renormalized. And the issue is that this is, if you think in particle terms, the graviton is a spin 2 particle. It's not spin 1 particle or like the photon or the half spin, half integer spins like the fermions. It's fundamentally more complicated. And by the way, this is the Lagrangian of the standard model. This is the most perfect theory of humanity. Standard model Lagrangian is verified up to the 10th digit in accuracy. So this is the best theory that we have, and this is the theory of gravity that we have. So it's impossible that this should describe it's the end of the game. You have a question or not? Okay. Now, the cosmological constant problem. If you think in QFT terms, then if you have the vacuum, of course, in the vacuum, you can have a creation of particle and antiparticle, and then the loop closes and it disappears to the vacuum. But this offers you an energy. So if you want to calculate the vacuum energy in quantum field theory, you need to sum over all these possible, so all species of particles, all these possible interactions that they are created from the vacuum and disappear in the vacuum. Right? This is how you're doing. So if you do that in the standard model of particle physics, you take all the particles, you found that the energy of the vacuum should be 120 orders of magnitude larger than the cosmological constant that we observe. Oops. Okay. And of course, apart from these two theoretical problems that GR cannot get quantized and what is lambda, now we have entered the golden century of cosmology. Why? Because we have the technological advance to do very, very accurate observations. If you think of that, 30 years ago, cosmology was a field in the edge of philosophy and general relativity. Typically you had a general relativity book, and as a last chapter, you had cosmology. Now it's a science, it's an accurate science. We have a huge amount of data, more than any other science in the world. That's why People are saying that the 21st century is the century of cosmology, in the same sense that the 20th century was the century of particle physics and nuclear physics. We have more than 100 space telescopes. We have opened the gravitational wave window, and we are observing gravitational waves. And of course, we have huge telescopes on Earth. And these observations bring us new data, more accurate data, right? We are living in the eras of 1859, that the advance of technology brought us the new data of the anomalies in the perihelion of the Mercury's motion, 43 arcseconds per century. But people were capable of measuring that. So now we can do very, very precise observations. And what do they tell us? First of all, H naught, it's the current value of the Hubble function. What is the problem? It seems that the universe expands faster than the predictions of Lambda CDM cosmology. H naught seems to be higher than the one predicted by Lambda CDM. So if you take Lambda CDM and General Relativity and you make the calculation, the value of H naught you obtain is 67 kilometers per second per megaparsec. Now, if you don't care about cosmology and you just measure directly how fast the galaxy is expanding from us, so a direct measurement of H naught, independent of the cosmological of cosmology, you find 72 kilometers per second per megaparsec. The difference is more than 5 sigmas. So H naught tension tells you that the predictions of Lambda CDM and General Relativity are wrong. And the universe expands faster than expected. I will come on the solutions. Of course, in order to solve that, you need to change something. Either that the universe has extra particles or extra interactions, dark matter interacts with dark energy or with baryons, etc. Or that you have non-zero curvature, or that your gravity should be modified. Qualitatively, let me give you the idea. If gravity is weaker than general relativity, it means that the universe expands faster. You see? Of course, you need to do that correctly at suitable scales, but this is the idea. Weaker gravity, faster expansion. But clearly, the H naught tension is very, very severe. The second tension has to do with perturbation. So H naught is related to the background universe. Sigma 8 is the quantity related to perturbations. Where is the problem? The problem is the following. This is the perturbation. This is the real universe. I can measure sigma 8. I can measure the spectrum here. The problem is that the universe seems to cluster less than the predictions of Lambda CDM. So you take Lambda CDM cosmology and general relativity, and you calculate the spectrum. This is what I did you before. And I said this is in agreement with the data. Yes, up to 10 years ago, it was in perfect agreement with the data. But now we have more accurate data. And you start seeing a disagreement. The large-scale structure of the universe is less than our predictions. And this is the famous sigma 8 tension. It's not so severe as the H naught tension, but it's still there. And of course, in order to solve that, again, you need to change something. You should assume that dark matter is hot instead of cold, or there are interactions or different structures, different clusters, or modified gravity. Again, gravity determines how fast matter clusters, because matter clusters through the gravitational self-interaction. Okay. If I have weaker gravity, it means that matter clusters in a less severe way. So again, qualitatively, you can see how modified gravity can solve you sigma 8 tension, right? Now, according to the James Webb recent observations, there seems to be too many galaxies too early. This is another tension. And there is also the cosmic dipole tension. Remember, the CMB radiation is completely isotropic. And also the smaller anisotropies are smaller perturbations. But according to the data, there seems to be a dipole tension. So in the half of the universe, you obtain different CMB spectrum than the other half. This is the dipole anomaly. And of course, we have a possible lensing anomaly. So you know what are the gravitational lenses, right? When you have a source here and it passes through a potential well, this observer in Earth sees that this source are two sources because one follows that path, one like that, right? And again, here there are some anomalies. So if you put all this together, we have what we call the new crisis in cosmology. So although Lambda CDM and General Relativity were extremely good to describe all the data till 10 years ago, the more accurate data that we have now put some tensions. Plus, we have the two theoretical problems, the non-renormalizability of general relativity and the cosmological constant problem. Something is wrong, and we need to change things. So I will stop here, and tomorrow we will start departing from general relativity and building modified theories of gravity capable of solving these issues. So are there any questions? Ask me everything. I will ask you if you don't ask me. Okay, so remember to do the calculations that I ask you. Make the variation of general relativity and give me the field equation. Start from the Einstein-Hilbert axion, do the calculation, and give the general relativity result. And it takes 45 minutes. And then, of course, if you have time, you can do the second step and take the field equations, plug in the FRW metric, and give me the Friedmann equations. This is the second step. So I think if they have time, they could do it for tomorrow, right? But we need to complete all the homeworks, okay? Okay? Yeah. Good. Good, good. It's a motivation for you. Okay. And then, yes, do you have any question? You can do it in Spanish, okay? Portuguese. I'm sorry, Portuguese. I don't know. Okay. But if you don't have a question, you can do after that. We are going to have time, Professor. Yeah, I will be here. Yeah. Don't worry. Okay. Don't be afraid also. And then, yes, thank you very much. Thank you. Thank you. Yes.